Good evening, everyone. So let us get started. So yesterday, the last class we started with the discussion on how to realize or how can we get a rotating magnetic field from rotor by not passing a DC current. That is the case for the synchronous motor. So we started uh, with this asynchronous machine. That is where we put AC current into the rotor. So you can see that the rotor was unexcited, and we have injected some current in the stator in the rotor winding, which has three-phase distributed winding. Now, if it has a it is sinusoidal current of 10 hertz frequency, then we saw that we get, if the rotor is stationary, then we get a rotating magnetic field that is at at basically 600 rpm. 600 rpm is corresponding frequency for the 10 hertz electrical excitation. so uh, if we then make the rotor rotate, when we inject the same 10 hertz current into the rotor, then the rotor itself rotates by 200 to 2400 rpm, and with respect to rotor, the rotating magnetic field, or basically the magnetic field of the rotor, that also rotates at 600 rpm. So it is like rotor, this is rotor, this itself is rotating at 2400 rpm, and someone, that is the rotor field, that is rotating at 600 rpm, and this is with respect to rotor. This is the rotor field fr. Then if someone is standing, say this is stationary, then what is the speed of the rotor with respect to the stationary person, that is 2400 rpm, and what is the speed of the rotating magnetic field of the rotor with respect to the stationary person, that is, because they are rotating in the same direction, so that becomes 2400 plus 600, that is 3000 rpm. Yes, so if we have seen that if we excite the stator winding with 50 hertz current, then the rotating magnetic field that is generated by the stator, that also rotates at 3000 rpm. So that is how we get two fields, one because of the stator, another because of the rotor, both of which are rotating at same speed, that is 3000 rpm, with respect to a stationary reference frame, that is they are stationary with respect to each other. If at any given instant the rotor field is somewhere, say rotor field is here, then at that instant stator field may be somewhere else. Stator field may be somewhere else. It may be leading that or even lagging that. We'll see all those cases. Yeah, sir, you can go ahead with your
Yeah,
question. You had some question on 41 slide.
correct. Here only. So the thing is
Yes.
now, yeah, 600 RPM, like when I excite my rotor with a stationary field, right?
No, when I excite my rotor with 10 hertz current.
10 hertz current.
Yes.
So, yeah, okay, there is no rotation, just a field only creates and it is running at 600 RPM, correct?
Yes. Yes.
Now, like rotor. Now I have given excitation to my rotor with the same 10 hertz AC current. Okay.
Yes.
Now you are saying that 2400. Now like why 2400? Like how it is been calculated like 2400?
No, I'm just giving some example. So
And
as of now,
yeah,
as
normally
a
yeah, normally with the 50 hertz, if I with the 50 hertz, normally the speed is 3000 RPM, right? Normally.
yes. So
So
if
now
stator
for 10
frequency
hertz,
is 50 hertz, yeah. Let me clear it up. If stator current frequency is 50 hertz, then the stator field that rotates at 3000 rpm if it is a two pole
Yeah, that
machine.
is clear.
Yes. Yeah.
Yeah.
Then.
This is clear, but the thing is
Okay.
now, you mentioned that at 10 hertz, 10 hertz AC current, you are exciting the rotor. So
Yes.
then it is 2400 is the one case. And again, in normal stationary, like just once you excite the rotor with the same 10 hertz, so 600 RPM is the one. So both are in relative. So we'll add it. So that is understood like it is having 3000 RPM. But
Yes.
I'm not getting 2400 where like and 10 hertz that linking.
No, I'm just giving
No,
an example. I'm just
he is
giving an
considering
example.
as an induction motor. Then he is explaining all this. He also
No, no,
assumed that
I'm.
it is running at 2004 RPM rotor. Then
I'm
for 10 hertz, this is how it will look like.
yeah. I'm just
All
giving
10
an
hertz,
example.
2400, all are random numbers he chosen.
Yeah, yeah, yeah. All these are random numbers. I am just showing that if how to get a 3000 rpm rotating magnetic field from the rotor with respect to the stationary reference frame. I'm just coming up with some numbers. So finally my speed has to be 3000 rpm because my stated excitation is 50 hertz, right? So I can have any numbers. Uh, I can have 2000 plus 1000. I can have 2400 plus 600. I can have 2800 plus 200. All these are possibilities. I am just taking an example of some random numbers, say 10 hertz and 2400 rpm, to show that the rotor magnetic field can rotate at 3000 rpm for this kind of scenario, that when we excite the rotor with certain frequency and if we run the rotor with some other speed, then if their summation is same as 3000, if somehow their summation of the speed is 3000 rpm, then we get what we do. So there are n number of possibilities with which we can get the 3000 rpm. This
But
is just an
generally,
example. Yeah.
yeah, that is generally whatever the excitation we give to the rotor is a 10 hertz normal. Not yeah, you told that that is some random number. So
Yes.
like in actual case, it is a 50 hertz only, right?
Which one? In actual case, the rotor excitation is never 50 hertz. Rotor excitation is far low. 10 hertz is an or over what should I say, very high number, high frequency value for rotor. Generally it is how much slip is only 3%, 4%. So yeah, as of now at this point of time, do not try to relate with something. I'm just giving or coming step by step how why does an induction machine operate on the first principle based on the two fields. That is what I am trying to discuss.
So no,
I
I
we
can
will relate.
I
Mm.
okay. Yeah, okay, okay. You can continue. Okay.
Okay, sure. If you have any further question, you can ask now also. Anything else? You
Sir,
got right.
here,
These are
here,
random numbers.
so here you marked conductor ROB, but in case of squirrel cage induction motor, what conductors are what conductors are belongs to Y phase, what conductors are belongs to the B phase? How
We
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 can
will we will
identify?
come to we will come to squirrel cage motors this class itself.
Okay, okay.
Yeah. So we saw that it is possible to create a rotating magnetic field from the rotor of the same speed, that is 3000 rpm, by maintaining that relative speed, that is rotor field will rotate at some speed with respect to rotor, and if rotor itself rotates at some other frequency, some other speed, and if the summation is equal to 3000 rpm, then our purpose is done. So that is clear as of now. Now we try to understand, is it actually necessary. So in this case what did we discuss till now? We understood that we can create a rotating magnetic field from the stator by giving some three-phase current excitation into the stator winding. In order to generate continuous torque, the rotor field also needs to run at 3000 rpm for this specific case. So stator we are giving 50 Hz, so the Fs that runs at 3000 rpm. For steady torque production, the rotor magnetic field, that is Fr, that also has to run at 3000 rpm with respect to, both are, all are basically with respect to some stationary person like us. We are stationary while looking at all these field simulations, animations. So now we can make it run, or we can realize this rotating magnetic field of rotor at 3000 rpm by giving some excitation, say, as I took in that case 10 hertz, that corresponds to 600 rpm. And if we, that is say, in the anticlockwise direction, and if we make the rotor run at 2400 rpm in the anticlockwise direction, then what is the relative speed of the stator, of the rotor field with respect to stator? That becomes summation of 2, that is 3000 rpm. So we are getting what we wanted for steady torque production. Now my question is it actually necessary to give two excitations in this case? So that we will see by putting some coils in the rotor, as we have put in the last case also. For simplicity, we'll just put three coils. That is, this is one set of coil, one terminal is cross, another terminal is dot. Then next set of coils, which are 120-degree shifted from the first set of coil, and then the third set of coil. We are having this three set of coils in the rotor, right? This is wound, so this is a practical coiling that has been done, and there is no current we have injected into the rotor, so the rotor has no current. We tried to see yesterday or the last class what happens to these coils when the rotor is basically stationary, and uh, we excite the stator with stator is excited with 50 Hz of frequency. This is the animation that will show us. So initially this is the field axis, right? Now as I run the animation, you will see that this will start rotating, as we have seen so many times. So what does it actually mean? It means that you can see, if you focus on these conductors, if you focus on these conductors at this point of time, they are linked by some flux lines. If I run it, and I will stop it, yeah, it is running. Now if I come to this point, you can see that the axis of the magnetic field is on the conductors, basically. That means this coil axis, which is perpendicular to this is the coil axis, and the magnetic field axis, this is the stator magnetic field axis. They are perpendicular to each other. That means no flux line is linking the coil. Whatever flux line, flux linkage of this coil is 0, right? As we go on, now you can see that at this instant the axis the magnetic field axis is aligned with the coil axis, but it is in the opposite direction or same direction based on the reference direction of the coil axis. So say if we consider this side to be cross, as we have done, that is some reference direction of current. So if this is cross and this is dot, then this is the coil axis, and at this instant the magnetic field axis, which was earlier here, now has moved and come here, getting aligned with the coil axis. That means all the flux is linking the coil. That means the flux linkage is maximum. So earlier when magnetic field was here, that is whatever I am trying to draw with blue color, then the coil magnetic field axis was perpendicular to the coil axis. That is why flux linkage was 0. Now after some time, the coil axis and the magnetic field axis, they are collinear. They are having 0 degree angle at the in between the two. That means magnetic flux linkage is maximum. Now if I run it further, after some time again you will have some time instant where the magnetic field axis which has now come here, that is perpendicular to coil axis again, so flux linkage is 0, and after some time it again will align, but in the negative sense. That is, magnetic field is here, coil axis is 180-degree opposite to that. That means again flux linkage will be maximum, but it will be negative. So we see that if we excite the stator with 50 Hz current and do not do anything in the rotor, but just try to see by putting some rotor conductors what is the flux linking the rotor, then we will be able to see that basically varies with time. So like this is 0 degree, or this is time equal to 0, and I will just indicate the R phase. So this is, so what did we take in the earlier case? This side is cross, this side is dot. So the same thing we will take here. This is cross and this is dot. That means this is the coil axis, and initially the magnetic field axis is here, right? This is the magnetic field axis. Now you can see that magnetic field axis, if we take two components of the magnetic field axis, it is basically the component that is perpendicular to that is actually opposite to the coil axis. That means the flux linkage of the R phase is actually negative. That is what you can see here. Flux linkage of the R phase is negative when we start from 0. Now after some time, when we move by some angle, then at this instant, probably 4.5 millisecond if it is visible here, then it reaches 0, because the magnetic field axis which now has come here is basically perpendicular to the coil axis. So the angle between the two is 90-degree. So if we take the component of the flux magnetic field along the coil axis, it is cos of 90-degree, that is 0. That is why we have 0 flux linkage at this instant. Now if I go further ahead, at this instant you can see that the magnetic field has rotated and come here. So at this instant the magnetic field is aligned with the coil axis. So we have reached this point where our flux linkage R coil flux linkage is basically maximum, and the same phenomena will repeat as the magnetic field, stator magnetic field will keep on rotating. Now because we have put two more conductors, two more coils, so this is basically the R coil axis. Similarly, we have put some B coil axis and C coil axis also. So if this is R coil axis, uh, this will be which color I have taken. So this will be cross of Y color and this will be dot, right? So what will be the direction? So this will be our Y coil axis, and similarly we will also have our B coil axis, which will be here. So because the R coil axis, B coil axis and C coil axis, they are shifted in space by 120 degree, so the flux linkage of these three coils, we are able to see that they are also shifted by 120 degree. Now because flux linkage is varying with time according to E equal to d psi dt, that is electromagnetic, that is EMF, electromotive force in induction, basically electromagnetic induction, the principle of electromagnetic induction, E equal to d psi dt, that is there is some induced EMF if the coil is having some change in flux linkage with time. That means in all these coils we will have some induced EMF. We can see for we can we because differentiation will make the EMF lead the flux linkage by 90 degree. So you can see that in this case if I plot the R phase flux linkage only, the red color, you can see that R red color one I have taken, and if I plot the induced EMF, induced voltage in the R phase, you can see that that is also a sinusoidal quantity. And what is the frequency? Now let us try to look at the frequency. You can see that the frequency is same as the stated frequency, that is this much is 20 millisecond, that is 50 hertz. So we saw that this case, if we excite the stator with 50 hertz of excitation, then the induced EMF in the rotor phase, in case the rotor is stationary, we have some induced EMF of 50 hertz, that is same frequency. That is if the coils are shorted, let's say they are shorted, they are just the two terminals, if this is one coil, say two terminals like this, say I make the two terminals short, so there is some induced EMF in the coil, so there will be some current, right? So there will be some current, and current frequency will be same as the induced EMF frequency. Induced EMF frequency in this case is 50 hertz, so current frequency will also be 50 hertz. If rotor current frequency is 50 hertz, then the rotor magnetic field will rotate at 3000 rpm, and stator magnetic field is already rotating at 3000 rpm, so there will be some continuous torque. So if we just inject some 50 hertz current, or for that sense any frequency current, into the stator rotor and place some rotor conductors, rotor winding, for now, as of now, some rotor coils, then there will be 50 hertz of induced EMF, first 50 hertz of flux linkage in the rotor coils, then 50 hertz of induced EMF in the rotor coils. That means that will lead to 50 hertz of current into the rotor coils, that will lead to rotating of the or basically a rotor magnetic field that is also rotating at 3000 rpm. So we have stator magnetic field that is rotating at 3000 rpm and rotor magnetic field that is rotating at 3000 rpm. So there will be some torque production. So your rotor will start rotating. So that is why, so that is the standstill principle, that yeah, even if you do not give any excitation to the rotor, just because of electromagnetic induction, there will be torque production and the rotor will start rotating. Now let us see what happens if, say, after some time of some rotation, the rotor speed has steadied at 2400 rpm. Say, why this speed? Again, I am just taking some random numbers. It can be 2800 also, 2900 also, 2000 also, based on the load. But now we are trying to understand. So now we have earlier we have understood that how torque is getting produced in the stationary condition. Now we will see what happens when the rotor is rotating at some speed. What about torque production? Now if I run the animation, again you can see that the stator, now it is, in this case also we are having the stator excitation only, rotor is not excited, and the rotor at 2400 rpm, some number. Let us try to see what is the flux linkage and induced, what are the flux linkages and induced emfs in the rotor coils in this case. If I bring those things, then we have three phases, three coils basically on the rotor, and we can see that it is still a sinusoidal quantity, a AC sinusoidal quantity basically, but the frequency you can see has reduced. So now you have one cycle is getting completed in 100 millisecond. Why 100 millisecond? Because that is the relative velocity of the rotor of the rotor coils with respect to the stator, with respect to the stator field, because the stator field is running at 3000 rpm. Now rotor, if I how to indicate, say this rotor is rotating at 2400 rpm. What is the coils are sitting on the rotor, so the rotor conductors are seeing the flux, sometimes linking fully, sometimes zero, sometimes negative. So they are seeing that the flux linkages of them are changing. What will be that frequency of change? That will be about the relative speed between the two. So that is basically 600 rpm, and that corresponds to 10 hertz. So that is what you see, that you have a 10 hertz of uh, 10 hertz of flux linkage in the rotor coils in this case. Now what will happen if we have 10 hertz of sinusoidal flux linkage? Then there will be some induced EMF in the coils also. Similar to the earlier case, I have just taken the R phase flux linkages, R phase flux linkage, and ER equal to D psi R dt. So the induced EMF will lead the flux linkage by 90 degree. That is what we see, that the blue one, that is leading it by 90 degree, right? So again, similar to the earlier case, if we short the two terminals of the rotor coils, then there will be some current flow in the rotor winding. And what will be the frequency of that current? That will be same as what is the frequency of the induced emf, that is 10 hertz. If we have 10 hertz of excitation, then the rotor magnetic field, there will be some rotating magnetic field due to the rotor current, so that will be 600 rpm, and this will be the speed of the rotor magnetic field with respect to rotor, right? So because the rotor is already rotating at 2400 rpm, that means again the same thing that we have discussed, rotor magnetic field will start rotating at 3000 rpm with respect to the stator. In this case also we are having some stationary or some stator field that is rotating at 3000 rpm, and rotor field which is rotating at same 3000 rpm with respect to the stator. That is so we have two fields, that are those are running at same speed, that is they are stationary with respect to each other, so we can have torque production in this case also. So we have seen that whether the stationary rotor is rotating or the rotor is still stationary, we need not give excitation to the rotor coils in order to have torque production in this case, because the induced EMF itself, if the coils are shorted, or the coils are basically shorted or uh, connected in star or delta or any other, the three phase connection is there, then the induced EMF itself will pass certain current, the same frequency current into that, and that itself will create a rotating field that is say at the same velocity with respect to the stator field. So that is why you can see that induction machine, although we can have rotor conductors, and we have the flexibility to inject some rotor current by some means, but we need not do that. So that brings us to, we have discussed that we can have two types of induction motors. One is the wound rotor, that is where we physically wind some coils on the rotor, and naturally, and we can basically short the three terminals, and that will take care of itself, or we can take the three terminals, if we take the three terminals out if we want to inject some current from externally, or we can simply, so we have the coils like this. So this is one coil, two terminals, already we are shorting these two terminals. Similarly, we have another, say Y phase, two terminals, again we are shorting, and we have B phase also, two terminals, again we are shorting these three terminals. So effectively, if we are shorting the two terminals of the R phase, Y phase and B phase, all the three phases that we have wound so with so much difficulty and pain, why not short all of them together from both sides? And if we are anyway shorting all of them together, what is the need to provide or complete this path like this? We can simply put a bar, put a second bar, third bar, fourth bar, fifth bar, sixth bar, and just short two sides with some ring. So effectively it will look like this. We have some ring, conductive ring, where some bars are coming and getting connected, and this is there on two sides, on both the sides. So these bars are going like that axially, and they are again getting shorted on the other side by another ring. So this type of cage we can put in the on the rotor, and still it will work. We will see how. So we will now get into the details of the cage rotor. So is there any question till now?
Yeah, Samrat,
Yeah,
can you go back to slide number 44?
44. Yes.
Yeah, here itself you have mentioned that principle of induction motor, right?
Yes.
Then why again you are going for the same?
The same means
Now you
in
are
the
going to
squirrel.
explain, right? Yeah.
Now I am going to squirrel cage motors.
Yeah, that
We
one
will
itself
see.
is a squirrel cage motor, right? In 44th slide.
This is not a squirrel cage motor. We have physically made this is like a turn. This is like a coil that we have made.
Okay.
So physically we have two terminals. So we can look at the flux linkages in those two terminals.
Okay. Yeah.
Now we
Yeah.
will go into the bars and see what happens in that case.
Yeah, you can go. Thanks.
Okay. Any other question? Okay. So we will get to the understanding of the cage rotor. So say we now nothing is designated, as someone was asking in the beginning. Say we have squirrel cages, how to identify which is corresponding to R phase, Y phase, B phase? Now you will kind of get the answer. So here nothing is designated, we just have some bars. So this is, I am telling B1, all these are having B2. So I'm just not, I'm for simplicity, I'm just highlighting some bars and naming them accordingly. Actually there are 30 rotor bars and they are numbered from B1, B2, B3, B4 like that up to B30, and I'm coloring only 10 of them, and for simplicity we'll be looking at the flux linkages and induced EMFs of the 5 bars only, because 10 plots will be too much complicated to look at. So we will just focus on B1, B7, B13, B19 and B25. All these are bars. They are not closed conductors like this, like the case we were earlier case we had. So we had conductor 1 on one side, conductor 2 on the other side. In this case we are simply having some bars and they are shorted on both sides. Okay, so
The number of rotor buses should be a multiple of 3, or we can use, let's say for 2029, can I use here? It will
yeah,
work.
yeah, yeah, yes, anything will work. So
But how
hmm.
that leads to 3 phases?
Yeah, we'll see that. Automatically it will lead to 3 phases. There will be some non-uniformity,
It's something
but
like a
it will
fractional
lead to,
winding,
yeah, something
right?
like fractional bending, you can say. You can say. But fractional winding you have, okay, let us not get into that. It may not be exactly that, but something like that, you can think like that. So for this case we are taking some reference direction. So let us say dot on all the conductors is assumed to be the positive direction, because we did not have any winding, or we do not because we do not have any winding, so we need not worry about the return path. So if one is dot, another has to be cross, we need not worry about that. Let us put dot reference for everyone. And now we will look at the case. Now what will happen, what happens if the rotor is rotates at 2400 rpm. So again you can see that the stator, we have some stator magnetic field, and that is rotating at 3000 rpm, and the rotor is rotating at some speed. It can be zero speed also, but because we have seen that zero speed or any speed that leads to the same phenomena, so better look at in the rotating condition. So what I have plotted what is the flux linkage and induced EMF for all the bars. So I have plotted for bar 1, bar 7, bar 13, bar 19 and bar 25, and the corresponding uh, induced EMFs I have put, right. So you can see that we have even same sinusoidal flux linkages. And how are they? So bar 1 is here, next is bar 7, that is lagging from bar 1 by some angle, and bar 13, next is bar 13, that is again lagging that by some angle. So this is how this is the case. So we have all these bars, and all these bars whatever is the angle. So if this is bar 1 and if this is bar 7, what is the angle between the two? Whatever is the angle, because this is two pole, the flux linkages will lag each other, lag the subsequent bars by the same angle. So if this is theta, this lag in time angle, that will also be theta, right. So because they are spatially shifted uh, in a symmetric fashion, with equal angles from each other, so the flux linkages will also be uniform or symmetric, and they will have the same lag between the two, that is theta, whatever the angle between the two mechanically, because this is two pole, the same angle will reflect in the electrical quantity such as the flux linkages or the induced EMFs. So we can see that all the bars are having flux linkages that are sinusoidal, and they are having induced EMF also, that is sinusoidal. So the induced EMF, if I just focus on the bar 1, so this red one, so same E equal to d psi dt, so that is leading it by 90 degree. So same phenomena we have seen. Now we will look at some instant by instant and try to understand. So let us uh, we will try to understand about the bar currents and what actually happens. So let us fix that t equal to 10 millisecond, that is this instant. At this instant the stator magnetic field is here, because we know that at t equal to 0 stator magnetic field starts here, that is right hand side x axis, along x axis. After 10 millisecond, that is half a cycle, it will come to 180 degree, that is here. So this is nothing but the direction of flux, that is flux lines. The direction of flux lines are like this. So from stator it is coming out, so this side will be north, and this side flux lines are coming into the stator, so that is why we have south here. Now let us try to see what happens in this case. In this case, as you can see, bar 13, is any flux line linking bar 13? Let us try to see by uh, drawing some flux lines here, which are already there. So this is one flux line. Surely this is not linking bar 13. This is say another flux line. This is also not linking bar 13. We can draw another flux line here. That is the extreme case. That is not that also is not linking bar 13. What do we mean by linking? It is not enclosing the bar 13. So at this instant bar 13 have zero flux linkage. Can you see that? So bar 13 corresponds to blue. You can see that we have zero flux linkage, right? Now let us see what happens for some other bars. So as I have already drawn some lines, you can see that this line is linking both bar 19 and this blue bar also, but that is not named in this case. So bar 19. So bar 19, what is the direction? Because this is the direction is like this, so the arrow will be like this. So this is clockwise. This is clockwise direction. All the flux lines on the top are clockwise. So the bar 19, that is also getting enclosed clockwise. That means bar 19, if it had dot current, then the flux linkage would be anti-clockwise. That is the reference direction for positive flux linkage. But here the actual flux linkage is clockwise. That is, we have to understand that the bar 19 should have negative flux linkage. Now let us justify it by looking at the plot. So at this instant, where is bar 19? That is this pink one. You can see that pink one is actually here, that is in the negative side. So you can see that bar 19 is having negative flux linkage. So if bar 19 is having negative flux linkage, if I plot some lines on the bottom side, so this is one sample line that I have plotted, right? What will be the direction? I have already indicated the direction of the stator field, that is in this case it will be anti-clockwise. So all these bars, like this bar 7, bar 1, all these are having positive flux linkage because some flux lines are linking them in the anti-clockwise direction. So they should have positive flux linkage. That is what you can see. Bar 1, that is here, it is having some positive flux linkage. Bar 7, that is also having some positive flux linkage, and black one, that is B25, that is here. B25 is here on top, so B25 is having some negative flux linkage. So all bars in between are having flux linkage on this line. So if I plot flux linkages for all the 30 bars, then they will be phase shifted versions of each other by what is that, 360 divided by 30, that is uh, 12 degree. So we will have 30 sinusoids phase shifted from each other by 12 degree, because it is two pole case. Now the corresponding flux linkages also or the induced EMF can be seen. Now the interesting thing about induced EMF is it is not in same phase of flux linkage. Induced EMF leads the flux linkage by 90 degree. So because we had 0, so the corresponding induced EMF waveforms look like this, and at the same instant you can see that the coil or the bar which had, that is bar 13, which had 0 flux linkage at this instant, actually has positive induced EMF at the same instant. And similarly all these are having also some positive induced EMF of some reduced number, and these are having some negative induced EMF. Now these rotor bars, what are they? They are simply some bars like this. They are some conductive bars. They are having some induced EMF across the two ends of that bar. And if we have to represent electrically the equivalent circuit of this bar, what will be? Say the bars are shorted in some way, or so there is some there is something there is some return path for everything, because all the bars are shorted from both sides. If we just have to represent this bar, then what is that? Because the bar is made up of either copper or aluminum, some conductive material that will have some resistivity, it has some certain length, it will have some cross sectional area, so it will have some resistance. And similarly all the bars, they are having some flux linkages. So if they are having some flux linkages, then that means there is some energy stored in the magnetic field for these bars. That means they will have some inductances also. So all the bars can be represented as some resistance and inductance as RL circuit. RL circuit, they can be represented because of the resistance. Why in series? Because if this is the current, then whatever current is responsible for the resistive drop, that is this current, that same current is responsible for the energy stored in the magnetic field also. So that is why the same current has to go through them, and we have some series RL circuit that can represent the each bar from electrical sense. Now what is the frequency, what is the going to be the frequency of this current? That will be the same frequency of the induced EMF. Induced EMF, what is the induced EMF frequency? That is quite low, that is 10 hertz, or actually it can be in actual cases it can be 1 hertz or even far lower than that, because the uh, actually in induction machines the rotor runs at very close speed compared to the synchronous speed. So 1500 rpm motor may run at 14,000 1470 1475. So what is the 25 divided by 1500? So this is the ratio of frequencies. So what is that number? It is basically 1 by 60. 1 by 60 is a very low number. So if one is 50 hertz, so the rotor frequency is even less than 1 hertz. So in most of these cases, because the excitation current or the induced EMF, that is having very low frequency, so at that frequency the resistance of the rotor bar is very high compared to the, this is the rotor or the slip, whatever way you want to represent, and that is the inductive drop of the that this is the inductance of the inductance of each bar, and this is the resistance of each bar. So at very low frequency the resistance actually dominates. So it can be, each bar can be simply represented as a resistance when the speed is actually very close to the synchronous speed. The rotor speed is very close to the synchronous speed, that is, this frequency of the induced EMF is actually very low. If this is a resistive, this bar can be represented by a resistive network only, then whatever is the phase of the induced EMF, that same will be the phase of the current, because it is simply a resistance. Had it been some RL, then the current would have lagged by the induced EMF by some angle, whatever is the phase angle for that R and L. So because we have seen that it is reasonable to neglect the inductance of the rotor bars, so each rotor bar can simply be considered as some resistance. So whichever bar has maximum induced EMF, that same bar will have maximum current also, and whichever bar has 0, or basically the induced EMF scales to current at any given instant. So that we will try to see. So we have seen in the earlier case, in this case basically, that bar 13 is having maximum flux link, maximum induced EMF. So bar 13 will have maximum current also. So that is what I have put here with a big thick dot that represents the, because it is positive, that is why I have put dot current. And the bar opposite to bar 13, that is this bar, should have the negative, should have the opposite one, if the because they are 180-degree phase shifted from each other. So if I if it was drawn, I will remove a few things. So had this bar induced EMF be drawn, it would have been somewhere here. Some other color would be better. So had I drawn the flux linkage and induced EMF of the bar opposite to that, that is, what is that, bar 25, 26, 27, 28. So bar 28, if I had drawn that, then this bar would be there, because we understood how the flux linkages are. They are basically phase shifted from each other, and that is why, because these are opposite to each other, that is 180-degree phase shifted from each other. So if one is having peak, another will have negative peak. That is as simple as that. So because bar 13 is having positive peak, the thing opposite to that, that is bar 28, that I have to put cross. Now what about others? This red one, bar 1, that is the bar 1 is having some negative, bar 1 and this bar 25, they are having same induced EMF but of the negative thing. So bar 1 and bar 25 I have to put negative. Bar 1, bar 1 and bar 25 I have put same magnitude cross current, and similarly 180-degree opposite to that I have to put a dot current there, and similarly bar 19 and bar 7, if I go there, bar 19, bar 19 is here, bar 19 and bar 7, you can see that the induced EMF is actually lower than, in magnitude, that is lower than whatever induced EMF is there in the bar 13, and that is also in magnitude, that is lower than whatever induced EMF is there in the bar 1 and bar 25. So that is why I have represented the currents in bar 19 and bar 7 with a smaller size dot, and accordingly 180-degree opposite to that there will be some cross currents of the same magnitude. So similar, so in between also, in other bars also you will have currents of different phases. Now what is the effect of that? You can see that at this instant you have all these, this is like a, this whole thing, whatever I am trying to draw, all these bars will have dot polarity current of some magnitude, and all the right hand side ones, all the left hand side ones will have some current of the cross polarity, while maximum current is there at 0 degree and negative maximum current at 180 degree. That is the current distribution that we can understand for this case. If this is the current distribution, then what can we understand, what can we tell about the rotor magnetic field? We can simply use our right hand side rule and draw that it will be in the downward direction. It is in downward direction because this side, left hand side is cross and right hand side is dot. So if we apply right hand rule, the thumb will point towards the downward side. So the rotor flux direction will be in the downward direction, and if we look at the rotor surface, the downward surface, the flux line is basically coming out from the surface. So this is north pole, and uh, the top surface flux lines, because of the rotor flux they are coming into, so there will be a south pole formation in on the top side because of the rotor currents. So you can see that two uh, you have two magnetic fields. One is the stator magnetic field, that is here, that is the stator flux direction, and you have rotor flux direction downward, which are 90 degree with respect to each other, with respect to each other. What made that 90 degree? And we know that 90 degree is a good case, because 90 degree is the case if the two fields are quadrature with respect to each other, then sine delta is 90, sine delta is 90, so sine delta is 1, that is maximum. So if we have two fields which are 90 degree with respect to each other, that is quadrature with respect to each other, then we will have maximum torque production. So you can see that in induction machine, when uh, the rotor is basically running at very close to synchronous speed, where we can neglect the rotor bar inductance with respect to the rotor resistance, then ideally we can have a quadrature shifted to magnetic fields. Now let us try to understand, because this is which case, motoring case or generating case. Let us try to understand that by looking at the relative phase of the two magnetic fields. Now you may be confused to think that here the rotor flux, because the rotor is rotating in the anti-clockwise direction, so as I have indicated, it may seem, you may be uh, 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 shifted to think that the rotor flux is basically in this case compared to the stator flux, because the rotor direction is anti-clockwise, so this is ahead and this is behind. But we have to, in order to determine which one is leading or which one is lagging, we have to actually look at the field in the air gap, and we have to define some reference directions. So let us try to do that. Let us try to see which field is leading and which field is lagging in this case. So let us consider a circle in the air gap, right? Now let us see that, let us take a assumption that if flux is radially outward, then we will assign positive sign to it, and if it is radially inward, then we will assign negative sign to it. So let us draw this case. So this is the field, this is say 180 degree, this is 360 degree, that is 0, this is 0 degree, this is 90, this is 270, right? This is theta. What is this theta? Theta, this is theta equal to 0, this is theta equal to 90, this is theta equal to 180, and this is theta equal to 270. Now let us try to see the stator field first. Stator field, let us try drawing that with red. So it is a stator field that is like this. This is the direction of the stator flux, right? So you can see that at 0 degree it is radially inward. Radially inward means we have to assign negative sign towards it, and it is at the axis, so it is maximum, so it is negative maximum. At 90 degree it is 0, right? At 180 degree it is radially outward, so you have to assign a positive maximum sign towards it. At 270 degree similarly it is 0, and 360 degree again it is negative maximum. So it is a sinusoid like this. If I try to draw only the fundamental of it, because there will be some, if this is B, then there will be slot harmonics, as we have seen in the earlier case. So this is about the stator, this is about the stator field. Now let us try to look at the rotor field. Or stator field was blue, so probably I should make it blue here, and we will mark the rotor field with red. Now let us try to see the rotor field. Rotor flux direction is downward, that is flux direction is like this, flux direction is like this. So at 0 degree it is 0, at 90 degree it is radially inward. Radially inward means we have to assign negative sign towards it, so some negative value. At again 180 degree it is 0, at 270 degree it is radially outward, so maximum. At 360 degree again 0. If I join those, I can join those. So this is sorry, to remove that. So the red one was red is for rotor, and the blue one is for stator. Now if the fields, as we have seen that field moves in the anti-clockwise direction, that is this field is also rotating this way, this field, as we will see for other instance also, this field is also rotating in this direction, it is progressing in the positive direction. So which one is leading? You can see that the stator one, that is ahead compared to the rotor one. That is the stator one, that is leading the rotor one by 90 degree. So the stator one is leading the rotor one by 90 degree, means the stator one, the energy transfer is happening from the stator to rotor, that is it is motoring in nature. Now the same phenomena can be looked at the other instance also. So I'll quickly go through them. This is t equal to almost 15 millisecond. Consider it as 15 only. This So at this instant, this is how the flux linkages of different bars look like, and this is how the induced EMF look like. So this is the instant which we are looking at. This is roughly 15 millisecond. So we have here this bar 7 that is having 0 induced EMF. So by the same principle, bar 7 will have 0 current. All these pink one, that is bar 19, and blue one, that is bar 13, they are having positive induced EMF, whereas the bar 1 and bar 25, they are having negative induced EMF. So they can be appropriately given, assign some current towards it by with the same approximation that R is very greater than omega L. So B7, that is having 0, so 180 degree opposite to that. This one will also have 0, this one will also have 0. So B13 will have, B13 has some positive value, B19 also have some positive value, but B13 is significantly higher compared to B19. That is why this is bigger dot, this is smaller dot. This is also having some approximately same as B13. So similarly B25 has some negative current. B1 also has some negative current. You can see B1, that is black, sorry, red, that is having negative current, quite uh, closer to the peak, and black is also having some negative current, smaller than the red one. So B1 is having very high, very big cross current, whereas B25, that is this one, B25 has some lower amplitude but negative current. So in this case, we are having dot conductors on the top side and cross conductors on the bottom side. So the what will be the field direction? This is the field direction for the rotor. And again, if the same thing is drawn, one thing is you will be able to see which way are the fields rotating, and you will also be able to see that uh, stator still leads the rotor field by 90 degree in this case also. Now if we go to the 20 millisecond case, that is this instant where the field, stator field, has rotated 360 degree and again come back to the x direction, x axis. So this is south pole, this is north pole. Now again B1, the B1 bar, because there is no flux linking the B1 bar, so B1 bar is having, this is the t equal to 20 millisecond time instance, so B1 bar is having 0 flux linkage. So B1 bar should have negative, basically negative induced EMF, because it is going from positive to negative, the flux linkage. So it will be negative induced EMF, and accordingly the same thing, if we try to draw some flux lines as the previous case, similar to the previous case, here you can see that these are anti-clockwise. So the top side bars, they are seeing anti-clockwise direction of flux linkage, that is positive flux linkage. So B7 and B13, B7 green and B13 blue, all are having positive flux linkage at this instant, whereas the bars on the bottom side, that is B19, B25, B19 pink and B25 black, they are having negative flux linkage. So accordingly the induced EMF can be plotted, which are basically 90 degree ahead of the corresponding flux linkages. So accordingly current amplitudes, current directions can be assigned. So if you remember, for in the t equal to 10 millisecond case, we had all dot currents on the right hand side and all cross currents in the left hand side, but because we have moved ahead by 10 millisecond, that is that is equivalent to 180 degree electrical. So we have all the dot currents on the left side, all the cross currents on the right side. So this is the rotor flux direction. And similarly, if we plot the radial flux density distribution in the air gap, considering radially outward to be positive, radially inward to be negative, we will find that still the stator uh, stator uh, field is leading the rotor field. So this is about what happens in the rotor bar currents, and even though we have not completed the winding by assigning some by signal by telling that okay, this is R phase, this is B phase, we have not told anything like that, but equivalently you can see that in the stator, three phase distributed current that is producing a rotating magnetic field, and on rotor, in rotor bars, what is happening is the rotor bar currents are also sinusoidally varying in nature in space, so that is also causing a rotating magnetic field, and they are interacting each other to produce the torque. So this is about the motoring action, what happens during motoring. So probably on the next class we'll see that what happens during generation, that is when the rotor speed is actually more than the synchronous speed. Now we have taken the rotor speed to be 2400 rpm, that is lower than the 3000 rpm, that is the synchronous speed, the speed at which the stator magnetic field is rotating. Next we'll take a speed, say n2, that will be higher than 3000 rpm, and similar to this case we will try to look at the flux linkages and induced EMFs in the rotor bars, followed by the rotor bar currents, and we'll then look at the field, which one is leading, which one is lagging, and before that of course we will try to see how these currents of the bars complete their path through the end ring, and if we want to estimate the end ring currents, how we can, that is the next topic, that from where we will start next class, that is how to get the end ring currents from the rotor bar currents. So yeah, I will stop for today here. If anyone has any question they can ask, or we can close it for today. Any question? Any question from anyone? I will close.
No, Samrat.
Okay. Was it clear?
Yeah, it's clear. Yeah.
Okay. Thank you. Good night then.
Thank you.